All right. Hey, everybody. Just want to catch up with you here on a brief primer on chemical reaction rates, reaction orders, and also how we're going to be able to adjust those things for temperature. So, to get us started for today, what are we talking about here? We're really after a description of reaction kinetics, and this is how our reaction rates are going to change the concentrations that we see through time. So for today, I want you to picture that we have a simple batch reactor. You could think of this like a beaker or a jar that a reaction is occurring inside of. And if we were to watch this through time, we might have some initial concentration at time 0, and that concentration might change through time. So if we went back and sampled it repeatedly, maybe we would see something that looked like this dashed line. Maybe we'd see something that was linear but with a slightly different slope. Or maybe we'd see something in a different shape, perhaps exponential, as I've shown here in blue. So the idea of what we're going to do today is ask, how does this chemical reaction rate proceed? Right? If we've got A and B that are combining to turn into C, how will this reaction rate proceed through time? And our chemistry will tell us that the rate this reaction proceeds could be described this way, where the removal on the left-hand side, of course, has a minus, and the addition on the right-hand side has a plus. The brackets here, you'll remember, denote concentration of something. And what we're really after today is this K. The K, lowercase k, has units of per time. That's a descriptor of how fast this reaction proceeds, and that's what we're going to need to know to describe the systems that we're designing. Okay. Now, one of the most important things we start with is what order is the reaction. And we'll typically think of these as 0, first, or second. You'll notice we're skipping first for the next slide because that's one I want to talk in a bit more detail about. So a 0 order reaction might look something like this from our observational data, nice and linear if we plot concentration through time. And that equation would be described by a simple y equals b plus mx sort of linear fit. And just as a note here, I'm writing concentration at time equals 0 in orange, but we'll often describe this as C0, meaning initial concentration. And this one's pretty easy. The slope of that line is the reaction coefficient that we're looking for. One problem here, if we assume that this just proceeds linearly, every hour we go forward removes a certain amount of concentration, we can get negative concentrations, negative mass per unit volume. And we can't have negative masses, so this is physically not possible. So often a little bit too simple. 0 order, on the other hand, might look something like this, where the concentration remaining is dropping rapidly. And actually, if we plot 1 over concentration, as shown in the bottom right panel, what we see is a nice linear fit. And so in this case, the slope of that 1 over concentration through time describes our reaction order. The one that I want to focus on with the rest of our time here is going to be a first order reaction. Far and away, these are the most common way that we'll represent reactive processes. Our concentration time series has a characteristic exponential decay. And of course, that means if we plot the natural log of concentration through time, that's where we actually see that nice linear time series. Well, the exponential is described as I've written in the top left of the slide here. Concentration through time equals C0 times E raised to the minus K times T power. Well, the slope of that natural log of concentration through time, that's what gives us our reaction coefficient. One of the things that we're going to be able to do with any of our orders, but in particular we're going to focus here on first order, is generalize these. And what I mean by that is asking a question like, how long will it take to drop that concentration by 50% or 90% of what came in? And if we take our equation from above and we say, well, I want to know when the concentration is 50% of the input. So I've replaced the left-hand side with 0.5 times C0. Of course, C0 is on both sides, we could cancel that out. And what that actually means is that the initial concentration doesn't matter. These characteristic timescales are really useful to us because it doesn't matter what the starting concentration is. It will always take the same amount of time to remove half of that concentration, or to drop concentration by 50%. So we can do some algebra magic and turn this into an equation that says time equals minus the natural log of 0.5 over k. Or we can even simplify the top of it to 0.693 over k. So the idea here is that we can relate our reaction rate directly to a time scale. It's totally independent of concentration, and this can be really useful to us in a design context. Now, one of the important things we might want to know is, what is that rate coefficient and what order reaction do I have? And so I've pulled together sort of a simple table here, and I want to talk you through what I think is far and away the easiest. If we've got some observational data, times in the left-hand column in red and concentrations in the right-hand column. So those are kind of our given information. How can we figure this out? And so the easiest thing to do is throw your data into Excel and then make two new columns, one where you take the natural log of concentration and one where you take the inverse of concentration. So you can type those equations in, you can drag them down. With that information, I suggest you make three plots, one of concentration through time, the natural log of concentration through time, and the third being the inverse of concentration through time. With those three plots made, you can do a best fit linear regression on each of those. You can look at the goodness of fit, for example, the R squared, and whichever one of those three plots is giving you the best fit representation, or the linear equation with the least error, that's the one I would pick. And so in the doodles that I've made here, what I've shown in light blue, that natural log of concentration, that would have the best linear fit with the least amount of error. And so if I'm then interested in what is the rate coefficient, you can see from the table that my k is, for a first order equation, my k value is going to be minus the slope of that line, or the slope of that line is minus k. So now we know what order reaction we have. We've got a way to find a rate coefficient, and if the world was a kind and just place, we might be done, but there's actually one more wrinkle we want to make sure that we account for in this class, and that's changes with temperature. So as a sort of back of the envelope calculation, every time you increase temperature by 10 degrees C, you approximately double the reaction rate, but we can do better than that approximation. And this is work that was done by Arrhenius, and what Arrhenius found is that that rate coefficient K depends on a handful of things. So it depends upon the activation energy for the reaction we're interested in, a reaction constant that is specific to that reaction, the temperature T, and I'm noting here that that's in kelvins, so all of the Arrhenius work is done with temperature in kelvins, and then R is that ideal gas constant, which you've likely seen in a chemistry class. And so what Arrhenius found is that these reaction rates really depend on two things. One, perhaps unsurprisingly, what is the reaction that you're interested in? And I've kind of highlighted that with orange. And two, what temperature this is at. So as a general rule, again, as temperature gets warmer, we're increasing the speed that our reactions will occur. So what the Arrhenius equation does is it allows us to correct our equations to different temperatures. So the way that this turns out to be really useful to us, if we thought about two different temperatures, T1 and T2, having two different rate coefficients, K1 and K2, we could set those up as a ratio. And if we do a bit of magic, also known as algebra here, what we can do is we can take the ratio of those, K2 minus K1, or K2 over K1 equals this capital theta raised to the T2 minus T1 power. Now, what's actually happened here is that the rate coefficient, or the reaction coefficient A could be canceled out, and that e to the minus EA over R, that stuff all gets basically buried or recombined into a theta value. And so for any chemical reaction that we're interested in, any typical equation, we can actually look up that characteristic theta value. Right? And so that's extremely useful to us, because if we know a rate coefficient at a temperature, so K1 and T1, and we know the temperature our reactor is going to be at, T2, it lets us solve that problem for K2. So that's a nice, easy way that we can account for temperature as a control on how fast a reaction rate is going to proceed. All right, I hope that this primer helped remind you of some of the concepts that we might want to know out of chemistry, what these rate coefficients are, how to find them, how to temperature correct them. You've of course got resources in your text, and you are welcome to touch base with me if something in here is still giving you trouble. Thanks everybody.